Hi everyone, welcome to our part 2 of module 7, which is on concepts of Verilog HDL behavioral modeling. So at the end of this module, you will be able to understand the concepts of loops in Verilog HDL as well as conditional statements in Verilog HDL. So guys, if you have not subscribed this channel so far, or you are visiting first time to this channel, you can consider subscribing this channel so that you would be able to get more videos on concepts of VLSI. So now let's get started. So first of all, we are going to learn about the for loops in Verilog HDL. So similar to C++, for loops are used to repeatedly execute a statement or blocks of statements. And the important point is, if the for loop contains only one statement, the begin and end keywords can be omitted. Now let's see the syntax for the for loop. So the syntax of for loop is very simple, or it is similar to C or C++, where we have the for keyword, then the variable which will start from a value. So this is nothing but variable initialization, and then we have a condition put on that variable. For example, that variable should be less than or less than equal to or greater than equal to a particular value, and then we have the increment or decrement applied on that variable, and then we will have our begin and end keywords and the statements which we want to execute inside the for loop. So if we have only one single statement here, the begin and end keywords are optional. Now let's see one example for the for loop. So here we have a variable j which will initialize to 0, and the condition for the j is the j should be less than or equal to 7. Till then keep on incrementing the variable j. And the statements we want to execute is nothing but these are the statements we want to execute. So practically we want to execute these statements 8 times, because the loop here is going to execute from 0 to 7. That means 8 times these statements will get executed. Now let's see the second type of loop used in Verilog HDL, which is while loop. So while loop repeatedly executes a statement or a block of statements until the expression in the while statement evaluates to a false. So if you see the syntax of the while loop here, we have the while keyword and then the expression used here, and then again we have the begin and end keywords and the statements. Now the second point is, to avoid any kind of combinational feedback, a while loop must be broken with a condition here. For example, applying a @ or negative edge clock condition. So what does that mean is, so when we have this while loop in our design, until the expression evaluates to false, the while loop is continuously going to be executed. But in many applications we do not want this while loop continuously execute, but we want this while loop to execute every clock cycles till the expression evaluates to false, so that we get an expected result out of the while loop. So in that particular case, we can break the while loop by making use of some of the conditions. Like one example is by making use of @edge or negative edge clock, or we can also use some delay statements. For example, for simulation, a delay inside the loop can be suffixed. And if the loop contains only one statement, the begin and end keywords can be omitted. Guys, one important point here is, while loops are not recommended for synthesizable RTL. And the reason is, when we synthesize a particular HDL design, it basically gets turned into gates or registers. And in the case of while loop, if our design has a while loop, the synthesizer need to know exactly how many times the loop will execute, so that based on that calculation, the synthesizer can generate a particular hardware for that. So in case of while loop, since we do not know, or it is undeterministic that how many times the loop is going to execute, so it is very difficult for synthesizer to generate a netlist out of that Verilog HDL code. So while loops are not recommended for synthesizable RTL. Now let's see one example. So here we have a while loop, and then we have a overflow expression, or you can say this is a condition. So until the overflow conditions evaluates to false, at every positive edge clock, our variable a is going to increment by 1. So this is how we can use the while loops in Verilog HDL. Now let's see the another loop, which is forever loop. So the forever statement executes an infinite loop for a statement or block of statements. That means whatever is there written as the part of statements of a forever loop, that statements gets executed infinite time. And to avoid any combinational feedback, a forever loop must be broken with some conditions like positive edge clock. For simulation, we can also use delay inside the forever loop. And if the loop contains only one statement, the use of begin and end keywords can be omitted. So now let's see one example here. So we have forever keywords, then we have begin, and here at every positive edge clock, our A is going to increment by 1. And A is going to increment by 1 now for forever. That means for all the simulation time, our A is keep on increasing at every positive edge clock. So I hope this is clear. Now let's see one another type of loop used in Verilog HDL, which is repeat. So repeat loop is not synthesizable. The repeat statement executes a statement or block of statements a fixed number of times mentioned along with the repeat keyword. So here if you see, we have a repeat Verilog HDL keyword, and then how many times we want to repeat the loop which is mentioned here. And now we have our begin and end keywords, and then what all statements we want to execute. So if you see one example here, we have repeat to, then begin, and these are the two statements here, and then we have end. So basically these two statements are going to execute 2 times. So if you see here, when it starts executing, after 50 nanosecond, our A is getting 0. And then again 50 second, that means after 100 second, our A is getting a value of 1. And then again it will start repeating. So now 100 has passed. Again we will be adding 50 nanosecond here or 50 second here, and it will become 150. So at 150 again it is a 0, and then at 200 second or nanosecond as per the time unit, our A will be get a value of 1. So this is how the repeat loops work here in Verilog HDL. Now let's see one another important Verilog HDL construct, and it is very useful for simulation purpose, which is nothing but disable. So guys, if you remember in our previous part 1 of behavioral modeling, when we studied about begin and end keyword use case, there we saw that we can also use a named begin and end block. So to disable a particular block, we can use our disable keyword in Verilog HDL. So execution of a disable statement terminates a block and passes control to the next statement after the block. So wherever the simulation encounters a disable statement, it disables that particular block which is associated with that disable statement, and it passes control to the next statement. This is what the meaning of this line. Then it is like the C break statement. So disable is nothing but like a C break statement, except it can terminate any loop, not just the one in which it appears. So guys, very important point. So in C language, how break statement works is, suppose you have a loop, and on meeting some conditions in that loop, we want to break that loop and want to come out of that loop. So the break statement can be used only inside that loop, and it can just come out from that particular loop. But unlike C, in Verilog HDL, what happens is, suppose we are in one particular block, and in that particular block we want to disable one another block on meeting certain conditions. So by using the disable keyword, this can be done in Verilog HDL. We will see it in more details by making use of one example. And the important point, as we discussed, the disable statements can only be used with named blocks. Because if you see the syntax is disable and the block name. So if our block doesn't have any name, we cannot use the disable keyword for that, or basically we cannot disable that particular block. So here is an example. So here we have a block which has a name accumulate, and the statements inside this block is forever at every positive edge clock increment A by 1, and if A reaches to 7, disable accumulate. So what does this block do is, at every clock cycle it keeps incrementing variable A, and when the value of variable A reaches to 7, it disables this block. So this example is similar to the C break statement, but what else we can also do here is, we can also disable, suppose we have one another block here, divide. So we can also disable this particular divide block from this block. So for example, in this block itself, when the value of it is to 7, we want to disable this divide block. So here we can disable. So here what we are doing is, from one block we are disabling the another. So I hope this is very much clear. And also the difference in C break statement and Verilog HDL disable statement. Now let's see the next conditional statement, which is if else if else statement. So the if else statement executes a statement or block of statements depending on the result of the expression following the if. So whatever is the expression we have put in the if. So the else if statement is something like this. If we have expression, then some statements, else if we have some expression, then some statements, and at the last we have else. So the else if statement can be many times, but at the start we will have a if statement, and at the end we should have a else statement. So if the conditional expression in all of the ifs evaluates to a false, then the statement in the else block, if present, are executed. So if none of the expressions evaluates to true, the last statements which are mentioned in else clause will be executed. And there can be as many else if statement as required, but only one if block and one else block will be present. If there is one statement in the block, then begin and end statements may be omitted, and both the else if and else statements are optional. However, if all possibilities are not specifically covered, synthesis will generate extra latches. This else statement is optional, and even if some of the else if statement can be optional, but if those are not mentioned, then there is a possibility that the synthesis tool will generate extra latches in the design. We will see it in more details in next slides. Now let's see one example. So syntax, as I said, we have an if keyword, then the expression, then we have begin and end keyword and the statements, then we have else if expression and the statements, then more else if there are needed, there can be more else if, and then at the last we have else statement and the statements which needs to be executed. So now let's see one example. So if you see here, we have if ALU function is 0 0, we will be doing AND operation. We will be doing add operation. If ALU function is 0 1, we are doing subtraction. If ALU function is 1 0, we are doing AND operation. If ALU function is 1 1, so if you see here else, okay, else ALU is a divide function. So if you see here, our ALU function is a 2-bit value, right? So 2-bit value means it can be 0 0 0 1 1 0 and 1 1. So here we have covered our 0 0 0 1 1 0, and then only 1 1 is remaining. So this will we can put in our else part. Else means the value will be nothing but to tick be 1 1. So here basically we are covering all the possible combinations of ALU function. So in this particular case, since we are covering all the possible combinations of ALU function, that means there won't be any extra latches generated in the design. Now let's see another example. So if you see here, we have if A equal to B, if A and B both are equal, our X will be 1 and OT will be 1 1 1 1, right? So here we do not have any else condition. That means if A not equal to B, then what will happen? If A not equal to B, then this X and OT, these statements are not going to execute. That means whatever value was there previously for these variables, that same value is going to be there, right? That means basically the value is getting latched, and hence here extra latches will be generated in the design. So friends, a very important RTL design best practice is we should cover all the conditions which are possible in the expression. So if you see here, the ALU function is a 2-bit value and it can have 4 possible combinations. So we should cover conditions for all the possible 4 combinations. So I hope this is clear. Now let's see the next conditional statement in Verilog HDL, which is case statement. So the case statement allows a multipath branch based on comparing the expressions with the list of case choices. So what does it mean is, it will be more clear when we go through the syntax of case statement. But how the case statement is written in Verilog HDL is, we have case, then we have expression, and then we have case choices 1 2 3, something like this. So if the expression evaluates to 1, we would evaluate these statements. If the expression evaluates to 2, we should execute these statements, and so on. So the next point is, statements in the default block executes when none of the case choices comparisons are true. So we need to have a default case item as well. When none of our case choices matches, a default statement will get executed. With no default, if no comparisons are true, synthesizer will generate unwanted latches. So it is similar to if else if statement, where if we do not have a else part of the statements, our extra latches will be generated in the hardware. In the similar way, if we do not have a default statement and if none of our case choices matches, then again we are going to have latches in our design. So a good practice is to use a default statements whether we need it or we do not need it. If the defaults are don't cares, define them as X, and the logic minimizer will treat them as don't cares and save area. Case choices may be a simple constant expression or a comma separated list of same. So we will see it in more details in next example. So this is the syntax for case statements. We have our case expressions and then we have our case choices. So first choice, then we will have statements. Second choice, we will have statements, and so on, and then we will have a default statement, and then we have our end case keyword. So now let's see one example here. So if you see here ALU control, and the ALU control is of 2 bit. So if it is 0 0, the ALU output will be A plus B. If it is 0 1, the ALU output will be A minus B. If it is 1 0, the ALU output will be A and B. And default means whenever 1 1 is matched, right? If 1 1 is matched, then ALU out will be X. So this is one way of having a expression here. So here ALU control is a one signal of 2 bit. We can also use multiple signals here in the expression. So if you see here, we have a W and Y variables. So guys, I hope the both type of case statement examples are clear. Now let's see another type of case statement, which is CaseX. So if we use the CaseX statement, the Z value, the X value and a character match symbol will be treated as a don't care. So if you use the CaseX statement, when the case choices are nothing but these one. So when the case choices constants contains Z, X or a character match symbol, they match any values in the A. A is nothing but our case expression. You will understand it in more details when we will be discussing the example. Now the second point is with case A. With case a normal case statement, if A is equal to X unknown, it only matches a value of X in the case choices, and it will not match a value to 1 0 or Z. That means in the normal case statement, if in our case expressions a value X is present, that will match only a value of X in our case choices. It will not be considered as a don't care and it will not match to any other values. And similarly, if A contains a Z value, it will only match to a Z value. But the CaseX uses X as a wildcard which can match anything. Now let's see one example here. So we have here our CaseX statement and the expression is nothing but variable A. So if our expression A has a value of 1 0 or 1 1, it is going to match to this case item, because this case item is nothing but to tick B 1X, and since we are using the CaseX statement, so this X will be considered as a don't care and it can be matched to 0 and 1 both. So whether our A has 1 0 or 1 1, our case item first will be selected. That means MSB will be assigned to 1 if A equal to 1 0 or 1 1. If you see the difference, when instead of CaseX we have a case A. So if we have a case A, then this item, this 2 tick B1X will match only a value when A will have 1X. Then only this case choice or this case item will be selected. Now let's see the next case item. So next case item is nothing but 2 tick B Z1. So as I said, if we are using CaseX, both X, Z and character matching symbol are considered as a don't care. So here Z will be considered as a don't care. So this case item will be selected whenever the value of A is 0 1 or 1 1. So I hope this is clear. Now let's see the third type of case statement, which is case Z. So there is a small difference between CaseX and CaseZ, where in CaseX, Z, X and a character match symbol are considered as a don't care. But in case of CaseZ, only Z and character matching symbol are considered as a don't care. That means if our case item contains Z or character matching symbol, we can consider them as a don't care. But if there is a X present, that cannot be considered as a don't care. or that has to be matched with the expression value explicitly. So case Z is same as case X, expect only character matching symbol and G are used in the case choices constant as don't cares. Now let's see one example here. So here we have our case Z statement and expression is nothing but variable D, and the first case choice is 3 tick B 1 and character matching symbol, character matching symbol. So here what will happen is if B is equal to 1 0 0 or these values can be 0 0 0 1 1 0 1 1. So all these values, this case item will be selected because in case Z this character is considered as a don't care. And similarly here also this character matching symbol is considered as a don't care. So for both 0 0 and 0 1, that means 0 1 0 and 0 1 1, this item will be matched. So guys, I hope the basic difference between case Z and case X is clear, and here we are going to conclude on this part 2 of our behavioral modeling module. If you have any doubts, please write down in the comment section. Also, if you like this video, please hit the like button and do not forget to subscribe this channel and press the bell icon so that you would get notified as soon as I upload a new video. Thank you very much.